Alright guys, today we're going to look at two things that are going to be important to us in solving some problems and getting into the next level of understanding how you look at tension and different forces on bridges. Guys, when you go to engineering school, you'll take a class called statics, and you'll take another class, a class called dynamics. So we're going to be talking about how this relates to those classes as well. Tension is a really simple concept, but there's one misconception that kids bring with them quite a bit of times, so we're going to try to dispel that today. If we have a 10-kilogram weight just hanging, and I asked you what is the tension in the string, most kids get this right. They say, well, the weight of that 10-kilogram mass is 10 times 9.8 or 98 newtons. So therefore, there's 98 newtons pulling down by the weight. So what does the tension in the string have to pull up with? 98. Now most kids see that and they're like, Mr. Lennick, that's super easy. So the tension in this string right here would be 98 newtons. Seems pretty simple. Okay. If that's pulling down with 98, the rope needs to be pulling up with 98. Now, when we go to this little example though, and I ask this question, usually kids get it wrong. If this guy here is pulling with 50 newtons of force in a tug-of-war contest, and this guy's pulling with 50 newtons of force in a tug-of-war contest, what is the tension in that string? A lot of people answer that. They say 100. Because he's pulling with 50 and he's pulling with 50, they say 100. But the tension in the rope is what? 0. It is 50 newtons. Okay? Now, and I really want you to pay attention. If we were to draw a free body diagram right here, isn't there 98 newtons pulling down that way? And isn't the retention pulling up with 98 newtons? Are they pulling in opposite directions? Yes, they are. And there's 98 pulling down and 98 pulling up. But every kid says 98 newtons in the tension, and that seems easy. But then when we turn it sideways and we do 50 and 50, a lot of kids answer 100, which it's the same thing. So the tension in that string is going to be 50 newtons. Do you see that? Okay. And if we were to talk about how much tensile strength that rope could handle, if you were to get, let's say it's a 40 Newton tensile strength rope, you're going to do what to that rope? You're going to break it. Okay. Does everybody see that? Okay. But if it's a 60 Newton tensile strength rope, you're not going to break it. Unless you have a misconception that the answer is 100, and then you'd say it was broken, but it's not going to break. Everybody cool? Now, this is kind of another thing that's interesting that we'll talk about. I always ask this question. If we had the Dallas Cowboys offensive line right there, and then we had the Dallas Cowboy cheerleaders here, okay, and they were pulling in a tug-of-war contest, who would be pulling on the rope harder?
They'd be pulling the same.
Newton's third law says they'd be pulling the same. The big difference is not how hard you can pull on the rope, it's how hard you can push on the ground. And if you're more massive and you're harder to move because you have inertia and you have more friction so you can push on the ground harder, then you usually win tug-of-war contests. But you can't pull on the rope any harder than the other team can pull on the rope. And a classic example of that is, could the Dallas Cowboy cheerleaders beat the offensive line if the offensive line were on ice? They were trying to pull on ice. Okay, so kind of a common misconception. You cannot pull on a rope any harder than somebody else pulls on it, and that's Newton's third law, which we've already talked about. So do you guys have a feel for tension? And we'll be working this quite a bit, so you'll get a whole bunch of opportunities to look at that. Now, apparent weight, guys. Apparent weight is going to be, it's kind of a measure of tension. Okay? So in this case right here, this string is going to have a certain tension in it. Okay? And if we look, you're holding an elevator, and the guy's standing on a scale in the elevator. Okay? What's the scale going to read right there? Well, if this elevator is stationary, what's the scale going to read? It's going to equal its weight, right? Okay? So if it's stationary or it's moving at a constant velocity, the scale is going to read its weight. the person's weight. Now this kind of gets kids a little bit too. If I move that elevator up at a constant velocity, is it still going to read its weight?
Yeah.
Yeah, because the person is not being accelerated. It's moving at a constant. Does this make sense to everybody? And here's what I always kind of tell kids. If you get in an elevator, when it takes off, sometimes you can almost feel your knees kind of go like this a little bit. But once the elevator is moving, do you feel any different than you would if you were standing on the ground? Okay? So that kind of drives that home. If it's stationary or it's not accelerating, which means moving at a constant velocity, zero acceleration, the weight that you're going to get is equal to mass times acceleration due to gravity. Now, if we go into this situation and the elevator is accelerating up at 3 meters per second squared, then I think you would all agree that the tension in that string is going to go up. The force has to be bigger to accelerate it. Okay, and the scale is not going to read just the weight, but it's going to equal the weight plus whatever the mass is times how much more we were accelerating. So in this case right here, we take whatever the mass of the guy is times 9.8 plus whatever the mass of the guy is times, in this case, 3. Could you factor out the m's and basically say weight equals m times g, the quantity g plus a, effectively? Does this make sense? Okay. And guys, I think that's pretty straightforward. If I'm going to accelerate something upward, I have to put a bigger force on it. If I put a bigger force on it, there's going to be more tension in the string. And if there was a scale that the guy was standing on, would it push harder down? Would he push harder down on the scale? Okay. Now. And then in this example, instead of accelerating upward, and I left something off here, let's say we are accelerating at 3 meters per second squared, but we're going down this time. If you're accelerating downward, is the string going to have to pull up as much? Hold on, let me come back, because I think I lost them. Like here, if you're just holding it, it has to be equal to the weight. If you're accelerating it downward and you're letting it accelerate, you're not going to have to pull as hard on the string. There's not going to be as much tension. So the apparent weight is going to go down. And so really here you're going mg plus ma. But in this case, since a is going downward, it's a negative, which is going to make it subtractive off the weight or the tension that you're going to feel. What do you guys think? Does that make sense? Okay. And then the classic, and this is what we're going to talk about it a whole bunch here coming up. If you take, and I don't know, see the scissors, those are impressive right there, and you clip the cable, okay, what's going to happen to what that scale reads? Okay. Well, what's going to happen is the elevator is going to go into free fall. Okay. The scale is going to go into free fall. You are going to go into free fall. And when that happens, the scale is going to go to 0. Okay? You will become weightless or apparently weightless. Okay? When you are in space, a lot of people say this. When you go to gravity, when you go to space, there's no gravity. Totally and completely wrong. Gravity, we've learned, permeates the whole entire universe. As long as there's mass around, gravity's going to be pulling. When you are orbiting the Earth, what happens is you are permanently in this elevator that is free fall. Okay? The spaceship that you are in is falling. Earth's gravity is pulling it. And so you just happen to stay in free fall all the time. That's what orbiting is. You're in permanent free fall. Now, the spaceship's in free fall, you're in free fall, everybody's in free fall, everything in the spaceship is in free fall. And so what it appears that there's no gravity, but you're basically just falling permanently. So we call it microgravity. Okay, is the terminology that they use. Does that kind of make sense to you guys? Okay, so in that case, the scale is going to go to 0. It's going to read 0. Okay. So guys, that is tension and apparent weight in a nutshell.